Hello scientists, we're here today to do the Unit 3 lab. So let's click on Unit 3 and go to the net force area. Of course, we're going to practice the scientific methods of making observations, forming a hypothesis, performing an experiment, analyzing the data, and then communicating the results. Particularly, the goal for this lesson is demonstrate how different forces acting on an object influence that object's motion. We're going to look at how vectors add. If you've ever moved an object with someone, you know that if two people act on an object in the same direction, that helps. But if you're pulling against each other, that makes the move more difficult. We're going to pop into the virtual lab here. You can view the tutorial, but I'm going to begin the lab. And there'll be a moment here while it loads. This is what the lab looks like. There are various masses here. There's a spring scale to measure the weight of that mass. Remember, the mass is how much stuff there is. There's more stuff in this particular mass than there is here, but we want to measure how much gravity is pulling on that mass, and that's the weight. We're using a spring scale to see how much the mass pulls on the spring, and that will tell us the weight of the object. So we can take the first one here and put it on the spring scale, and we can read here that it says just about 20 newtons. That's the weight of this object, not the mass. There's a table on your lab sheet here that gives the weight, the mass in kilograms, and we'll have to figure out the mass in grams. And I'll show you how to do that in a minute. But first, let's look at the beginning of this lab sheet and fill out some of the first questions. This is what your lab sheet should look like, and you should get it from doc sharing. Doc sharing is the area in the upper right-hand corner of your course sheet. It's on a gray bar. I'll show you in a minute. If you can't get the this lab sheet from doc sharing, and the first thing you'll see on your lab sheet is this is a direct link to the virtual lab, but I showed you another way to get in. So we just looked at the spring scale that we were working with here. There's a picture just to remind you which lab you should be working on. Now, the goal or the question of this lab that we saw at the beginning was something about motions and forces acting on an object. So I want you to form a question about motions and forces acting on an object. You might want to ask something about how those motions and forces, what happens when you add or subtract them. Our next question is, what is the equation for weight? We want to know how gravity, the acceleration due to gravity, interacts with the object's mass to create weight. Let's go figure out what that equation is. Don't panic, the Wikipedia page has a lot of information on weight, but what we can see here is it's an SI unit. It's a system international. That's another way of saying the metric system. It's a metric system unit, and we use it in newtons. And the way we derive it from other quantities is we take the mass, that's the m, times the acceleration due to gravity. Now, what's the acceleration due to gravity? Well, that's 9.8 meters per second, but we're going to use 10 meters per second. We're going to estimate for this lab. So here we can type in the equation for weight. Weight equals mass times gravity. And I'm going to spell out the word gravity. I'm actually going to spell out the word mass here too. I don't want you to confuse the G for gravity with the G for grams. We will use 10 meters per second or 10 meters per second squared for gravity for this lab. So now we want to know how many newtons is a 250 gram mass. Well, in the equation for weight, this mass is in kilograms, and gravity is in meters per second per second. Now we have 250 grams, so what we need to do is take 250 grams divided by 1,000 grams that are in a kilogram, and we get 0.25 kilograms. So our mass is 0.25 kilograms. So we take that 0.25 kilograms, remember we're using the equation up here, kilograms times acceleration due to gravity, which for our purposes we're going to use 10 meters per second per second. And when we take 0.25 and we multiply it by 10, we get 2.5. You just move the decimal point. 2.5 newtons. Just as a quick reminder why we changed grams to kilograms, here's the official definition of a newton. That's the unit we measure force in, or weight in, and it's kilograms per meter per second squared. So anytime we have grams in this lab, we need to convert it to kilograms. For this particular situation, we are actually measuring the weight and having to work backwards to get the mass. So we know that the mass weighs, the first mass that we weighed at the beginning of the lab was 20 newtons. We take 20 and we divide by 10. We divided by 10 and we got the mass in kilograms. And then to get the mass in grams, you take kilograms and you multiply by 1,000. So we can go back and look at that black mass in the lab as well. Here is the next mass. We'll take the silver mass off. That was our 20 Newton mass. Here's a mass that's slightly less massive, and we can see that the weight is also less massive. That looks like about 18 newtons to me. So the weight of this particular mass, how hard gravity is pulling down on this particular mass on this particular planet, is 18 newtons. So you can fill that in on your table. What we want to do right now is see how these masses create forces, how the mass of the object plus the acceleration due to gravity pulling down on the mass, creates forces that act on an object. I'm pushing this go to the table here, and it says a target has been placed on the table. See if you can hit it with the center block by adding appropriate weights to each side of the table. Well, we'll see if we can hit that target. I'm going to grab a mass here, and while my other hand holds the block in place, I kind of drop it over the edge of the table and it automatically puts a string on it. Now, you know that if you tie a string to something and drop it over the side of the table, hopefully you know that this is just going to slide right over there. In fact, we'll just let go of it and you can watch that happen. Boom, off the table. Fortunately, cleanup's really easy here. We just reset the weights and start over. You might not have thought about what happens if two different forces act on something. Here are two different forces. Remember, the force is created by gravity pulling on the mass, creating weight. So now if we let go on the block, take a minute to guess where that block is going to head. There's a vector going this way, and there's a vector going this way. the masses of these two different objects here that are hanging off the edge of the table are pretty close. So their vectors are going to be of similar size. Let's see what happens when we have two vectors, two forces acting on an object at the same time. It doesn't go in the particular direction of one or the other. You can add the vectors. So here we can represent the pushes and pulls on the block with arrows. We know when we attached a mass here, it got pulled just in this direction. When we added the second mass, it also got pulled in this direction. And when you add those two forces, let's make this one a little bit smaller. When you add two forces like this, you add them tip to tail, the force that results is just going to be the two arrows added, and you draw from the tail to the tip like this to add those two forces. And we know the block slid off like that. If you want to know how to add the arrows, you go to your Insert, Shape, and then you can pick whatever you'd like here, block arrows or lines and arrows here. It's going to look a little different if you're working on a PC. Insert will be kind of more over to the left, but it's Insert Shape to get an arrow. I'm going to properly label my vectors right now. I'm going to take off the addition vector, put my vectors back where they go, and I'm going to get a text box here. This vector is 18 newtons because we massed it before we used it. That was the black one. And this one is 20 newtons of force. So I have two vectors there and they are labeled. And I know that the force they produce kind of went off up to the left-hand corner. Now let's work on problem number 4. It says attach a 250 gram mass to the left side. That's the smallest mass. Draw a diagram is viewed from above. Your diagram must have labeled masses and a vector showing force. So we'll add a vector to this diagram in just a second. We need to go into the lab and put a 250 gram mass to the left side of the block. So in order to get another mass, let's go over to the weighing area. I'm going to click on here, and we're going to get the smallest mass. How do we know it's the 250 gram mass? Well, we know it should have about 2.5 newtons of weight. So that looks about right. Let's take this mass, put it on our tray here, or our little cart, and go to the table. We'll take the smallest one. We'll ignore that. We want to go to the left here, and let's drop it and see what happens. It's not very massive, so it doesn't produce a great deal of force. Gravity doesn't pull on it as hard as a more massive object, and so it accelerates slowly, working against the friction of the block on the table. Alright, let's put an arrow in. We know that it went off to the left. And we know that 0.25 kilograms times 10 is 2.5 newtons. So I'm going to put in 2.5 newtons here. You can make this arrow a little bit, your vector a little bit wider if you want. Let's go through the rest of the lab and then you can finish it on your own. Going south would be going down, so make sure your vector is going here, down.